Okay, so we talked about how the law of cosines for very small values of a, b, and c, law of cosines on the sphere, actually does give you the classical law of cosines. And only approximately, of course, but that's true because even a small triangle on a sphere is only approximately the same as a planar triangle. So, however, these values are quite close. So what about the Pythagorean theorem? Well, from here, we're very close to a Pythagorean theorem. Because remember, the law of cosines is really like a generalized Pythagorean theorem. So, from this, we can assume, so what happens in the Pythagorean theorem, it's where one of the angles is right, yeah? And if you look at the planar situation here, the angle which would be right is, it's not sine gamma, it's cosine gamma here, sorry. It's law of cosines, not law of sines. So if you look at this, right, you get the Pythagorean theorem when gamma, this angle, is right. In this case, cosine gamma is 0, so you just get c squared equals a squared plus b squared. So what happens if we set gamma to be the right angle? Then on the sphere, we get this is 0. So that means the numerator has to be 0. Thus, so we get the Pythagorean theorem on the sphere. What does it say? It says that cosine C is equal to cosine A times cosine B. Compare it with the Pythagorean theorem on the plane that says something about the length of the sides. Of course, this also tells you something about the length of the sides. The angles disappeared from that statement, but it's kind of, yeah, it looks very different. The Pythagorean theorem in the sphere looks very different. For a small triangle, again, you should get exactly this. And I'm just going to do this calculation right here, but it's really just a repeat of that calculation we did for law of cosines, just in an easier case. So, small a, b, c, you get that this is 1 minus c squared over 2, and this is 1 minus a squared over 2. So approximately equal 1 minus b squared over 2. So you get that if you multiply everything out, you get 1 minus c squared over 2 is equal to 1 minus a squared over 2 minus b squared over 2, again approximately equal. The last term would be a squared plus b squared over 4, which we ignore because it's much smaller than the other ones. So you get that c squared is approximately equal to a squared plus b squared. Yeah, it's kind of interesting that this law here that looks very different, the Pythagorean theorem on the sphere, which looks very different from the Pythagorean theorem on the plane, actually is not that far off when you take small a, b, and c and just use approximation to these functions. You actually do easily get back to this Pythagorean theorem. Okay, this is definitely something to keep in mind. I think an interesting theorem that holds on a sphere and has very elegant shape, just like the original Pythagorean theorem. It's just that it's a very different shape. And for big ABC. Of course, this does not recover that theorem, but for small ones, it does, so everything is consistent.